Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's biweekly contest, make array empty. The problem is a bit difficult, but I would encourage you to stay till the end, and I'm very sure if you stick till the end, you will be able to grasp each and every concept that is required to solve this particular problem. So with that, let's get started. The problem states that you are given a integer array nums containing distinct integers, and you can perform the following operation until the given array is empty. The operation is, if the first element has the smallest value, you will remove it. Otherwise, you will put the first element at the end of the array. So basically, you are removing the smallest value one by one, and finally, the array would be empty. And now, because the array contains distinct numbers, there will be exactly one smallest element. So you are removing that particular element, and if the first element is not that element, you are moving that first element to the end of the array. You have to return the number of operations required to make the array empty. So for example, let's say this is the array 3 4 minus 1. Now in this particular array, the smallest element is minus 1. So you have to remove minus 1 from the array first. So you will see, okay, 3 is not the smallest element. So you will push 3 to the end. So the array would become 4 minus 1 3. Again, you will see 4 is not equals to minus 1, which is the smallest element. You will again push 4 to the end. So minus 1 3 4. Now minus 1 is the smallest element. So you will remove minus 1 from the array, and the array would become 3 and 4. Finally, you will see, okay, 3 is now the smallest element, and 3 is at the top of the array. So you will remove 3 as well. And now because 4 is the only element, this is the smallest element as well, and you will remove 4 from the array. So you require 5 operations to make the array empty, and hence the number of, like, the result here is 5. So hope the problem statement is clear. Now before jumping into solution, let's try to simplify it a bit. Let's say this is the array 1 7 minus 1 4 15 9. Now notice that you don't care about the values in this array at all. What you care about is which of these index you will remove first, and then which of the index you will remove second, and which of the index you will remove third, and so on and so forth, right? So in this particular case, you will remove the second index first, right? So this will be removed first, and then you will remove the zeroth index, because one is the next greater element, right? And then you will remove the third index, because 4 is the next greater element, and then you will remove the seventh, which is the first index. So basically, we are preparing this array where this denotes the order of indexes in which we will be removing the elements from the array. So let's just take an example that will make things more clear. So let's say this is the array. Basically, this is the order in which we'll be trying, which in which we will be removing the elements from the array. Now, initially, this is the state of the array. Basically, whatever was there at index 0 is at index 0. Whatever was there at index 1 is at index 1, and so on and so forth. Now, you have to remove the second index first. So you have to remove this particular element first. Now the index of this element is 2, right? It means there are two elements before this particular element, and hence you have to you have to make two operations, one to move this particular to the last, and then to move this particular to the last, and then finally this will be at the top of the array. So you have to make two operation to make this the top of the array, and then one more operation to remove this particular element itself. So basically you require three operation to remove two from the array. Now once you have removed two, three will be at the top of the array. So the index of this particular element, which was previously at index 3, is now 0, because this is now at the top of the array. So index of this particular element is 0, index of this particular element is 1, index of this one is 2, and then 3 and 4, right? Now you have to remove the 0th index. So basically we have to remove this particular thing. Now again same thing, the value here is 3. It means the 0th index currently lies at index 3, which in turn means that there are 3 elements before 0th index. So you have to remove all the 3 elements, or you have to move all the 3 elements to the last, and then you will be able to remove 0, right? So that's where you require 4 operation to actually remove 0th index. Now after you have done this 4 operation and you remove this 0th index, you will this array, so this element would be now at the top of the array. So the index of this element would be 0, index of this element would be 1, this one would be 2, and this one would be 3, right? Again, you have to remove the third index now. So third index value is 1. It means there is one element before 3 in the array, and hence you have to do one operation to actually make this third index to the top of the array, and then you will do one more operation to actually remove the third index. So you do another 2 operation to remove this third index. Now after you have done this, the fourth one will now be at the top of the array. So this would be 0, this would be 1, and this would be 2, right? Now you have to remove the first one, so you will remove this one. Now again, this means 2, which means there are 2 elements before this, so you will require 3 operation here. So hope you get the idea. You will just keep on doing this, and finally you will get the answer, right? Now we have to do this transition efficiently, right? So you can basically, once you have this array, you can actually figure out what is the values, how many operations are required to remove the indexes one by one, right? So the transition from one array to another is something you have to do it efficiently. Basically you can do this easily in order n, right? You can say, okay, second index is removed, so this would be 0, this would be 1, this would be 2, and then 3, 4, and so on, right? So this can be done in order n, and because you are doing n number of transition, so the overall complexity would be order n square, which would not pass because n is up to 10 to the power 5. So this transition is something you have to do it efficiently in log n or root n or something of that sort, right? Now, how to do this transition? So let's see what all changed here. So here what is changed is you have subtracted 3 from this range, right? So that is good. Like there is a data structure that can actually do range updates. Similarly, you have added 3 to this range. So that is also good. You can do range updates as well, right? Now, after that, you actually need to know what is the value at a particular index. So that is also good because you know that you can do point query as well. Now, think about this transition. Is this transition also straightforward? Basically, this 4 now becomes 0. So you have subtracted 4 from here, and this all remains as is. So basically, you will not be able to figure out a pattern here. So the pattern here, like this all is subtracted with minus 3 because the this is now the top of the array, right? And the index of this would now become 0. And because the index initially here is 3, you have to subtract 3 from everything in the right. So that is good. Now you have to add 3 here. Now why we are adding 3? Because you know there are 3 elements here, right? So after this index would come, or this element would come, and hence you have added 3 to all these things afterwards, right? But as soon as you go to the next one, notice that you have removed this 0 in this scenario. Now here you can't say that I will subtract minus 4 from this entire range, because that would make all of this negative, which is actually not the case, right? So Previously, what we have done is we have subtracted minus 3 in everything in the right. But here we have subtracted minus 4 only in this particular place. So this part is actually difficult and we want to avoid this. So what we have seen that if we somehow have the new index of a particular element, we can figure out how many operations are required. So only thing we need to know is what is the new index of, let's say, 0, because let's say you're trying to remove 0, so you have to figure out what is the new index of 0, right? So can you do this without actually making all these changes to the array? So let's say you have, you know that this is the start of the array, right? Now given that this is the start of the array, can you actually figure out what will be the index of this particular position in the array? I would encourage you to pause the video and try to think yourself for a moment how you will figure out the index of this particular element given that this is the starting position of the array. So hope you've thought about it. Basically, this is straightforward. We know that this is the start of the array, right? So this is the first last element, or this is the last element, this is the second last element, and so on and so forth. So basically you can just figure out the distance between this and this, right, and add n to it, because basically last element, it says that this is the last element, so last element would be n minus 1. So this is n minus 1, this will be n minus 2, and so on and so forth. So basically if you have to figure out the index of, let's say, this particular index I, and this is the start index s, the index here would be I minus s plus n. And similarly, if I is somewhere here, the index would be I minus s itself. So let's just take an example that will make things much more clear. So let's see this. So this is the initial state, right? Now what we are doing is, instead of making this 0, 1, 2, and 3 and 4, basically instead of making it the actual array indexes, we are just making it the indexes if this array is in the same order, right? So this element is now removed, so this will be the second one, this is the third one, this is the fourth one, right? So that's what we have done. We have simply updated this to 2, 3, and 4, and nothing else is changed. Now you have to figure out the index of this particular element, and this is the start index. Basically this is now the new start of the array. You have to figure out what is the actual value of this ith index. So what you can simply do, you can simply subtract I minus s and add n here, because like of the same reason we have discussed. This is the start index, so this is the last element, this is the second last element, and so on and so forth. So basically the distance between this denotes how many elements you have to skip from the last, and you can just simply do plus n and you will get the exact index of this particular element. So just to take an example, this is the array, right? And now if you have actually find out the indexes, this would be 0, this would be 1, this would be 2, this would be 3, and this would be 4, right? So basically this will be your actual indexes. So now you can see the value here is simply I minus s. So let's say this is I, right? This is I. So and s is also 2. Like I and s both are 2. So this index would be 0. Now if this is I minus s would be 1. So this is 1, right? Similarly, if this is I minus s would be 2, and this is 2. Now if this is I minus s would be minus 2, and plus n. N is number of elements. So there are 5 elements active in the array. So minus 2 plus 5 is minus 3, which is the index or actual index of this particular element. And similarly, if this is I, the value here would be 4. So hope you can see that we can easily figure out what is the index of a particular element if we simply know the start of the element, right? So now if you look at it, this is now simple. What we need to do now is we just have to remove -1 from the right of the array. That's it, right? So basically this element is now removed, so every index here would now be decreased by 1, and this is like a range update. So we are doing a range update, or subtracting -1 in the range s to n minus 1. Now once you have done this, and let's say you have to you have to remove 0, you can simply apply this particular formula and figure out what is the actual index. So in this case, I minus s will be 0 minus 2 plus 5, which is 3. So here the actual index is 3. So the number of operation required would be plus 4, right? So 3 index is 3. It means there are 3 elements before this index. So the number of operations required would be plus 4, right? Similarly, once you have removed this particular element, so everything in the right would now be decremented by 1, right? So we have just decremented everything by -1. So 0, 1, 2, 3. So notice that this element here doesn't actually matter. So even if it is -1 or -2 or anything like that, we don't care. Now after we have done this, this is now the start of the array. So this is now the s, right? Now we have to remove 3. So this is now I. Again, I is greater than s, so we can simply do I minus s to get the actual index here. So the actual index here would be 1 itself. I minus s is 1. So basically it means that there is one element before this, and hence we will require 2 operation to remove this particular index. Now once you have removed this, you will subtract -1 in this range, right? So this will now become 1 and 2, and this is the next element, which is this, is now the new start index. So this is now the s. Now you have to remove the first one, so this is now I. Again you will see I here is less than s, so the value here would be I minus s plus 1, s plus n. So n here is 3 because there are only 3 active elements, right? So I minus s is 0 minus 1, which is -1, and plus 3, which is 2. So the actual value or actual index here would be 2, which means there are 2 elements before this particular index, and hence you will require 3 operation to actually remove this particular index. Now after you have removed this, this will be the next index again, right? So this is now again s, and you have to now remove fifth one, so you have to remove this one. So this is now I, and because I is greater than s, so the value here would be I minus s, which is plus 1, and the operation required would be plus 2. And finally this is the only array, and required operation will be plus 1. So hope this entire algorithm makes sense. What we, like, just to reiterate the entire thing, what we are simply doing here is we we saw that only thing that matters here is the index of the elements. It doesn't matter what is the value at that element is. We just need to worry about which order we will be removing the indexes. So we just try to do a dry run, and we saw that if we somehow know the new index of the element, we can simply figure out how many operations are required in each transition. So to figure out the new index of the element, we saw that we actually don't need to change the values of the indexes completely. We can simply maintain the the sorted indexes value, and we can apply this formula I minus s plus 1 and I minus s to figure out the actual index. Now once we get the actual index, we know what is the how many number of operations will be required for this transition. Now each of this transition, what we are doing, we are simply figuring out, we are doing a one constant operation to figure out the actual index. Once we have figured out the actual index, we can simply add that to our result, and then we have to subtract -1 in the right side of that particular index. So what we have to do, we have to do two things. One is range query or range update will be subtract minus 1 in this range L to R, and then we have to figure out what is the actual value here, right? So basically range updates and point queries. So both of this you can do via segment trees. If you don't know about segment trees, there is already a series that we have started in which we are trying to dissect segment trees from scratch. If you are not following that, I would strongly encourage you to watch that. We already discussed a couple of things starting from scratch, and we have solved a couple of different problems as well. And we are mentioning a sheet of different practice problems so that you can strengthen your understanding about segment trees. So I would link that playlist somewhere in the description or top right eye section. You can check that out if you don't know about segment trees. So with that, this is now the entire algorithm is. So let's just look at the pseudo code, and then we will look at the actual code. So the pseudo code is very straightforward. Let's get rid of this thing. So the pseudo code is straightforward. We remember we have to first build this array, right? So how we have built this array? We have like this is actually the index of the sorted array. So this is the index of the smallest element. This is the index of the second smallest element, and so on and so forth. So how we can figure out this array? You can simply create a array of like pairs and then sort it. And after you have sorted it, the actual indexes in this array would actually denote this particular array, right? Now, after you have like figure out this array, we have to just maintain a starting index s, right? And we know that this is the index we have to remove, right? So this index is actually this particular thing. So this basically this index will denote that I have to remove 3. So index value here would be 3, right? But this is actually not the value after you have done some updates, right? So to get actual value here, you have to query the segment tree. So you just query the segment tree for that particular index, and you will actually get the value of I, right? Now, once you have get the value of I, you can simply apply this formula I minus s plus 1 or I minus s to actually figure out the exact index, and you can simply add that to your result, right? And after you have done this, notice that what we have to do, we have to simply like add minus 1 to everything in the right. So that's what we are doing. We are simply adding minus 1 in the range index 2 and minus 1. Now notice here we have chosen index instead of I because we have to do minus 1 in everything starting at 0, not at the actual index. So basically here we will be doing minus 1 for 4 comma 5, not at 1 comma 5, like not at this I would not be the actual value. This we have to do minus 1 in this range, which is index comma and minus 1. Now after you have updated this, the next thing is to update s as well, right? So the value of s would actually be the next available element. So in this case, let's say you have removed this particular index, so the value of s would be this because this is the next available index. Now there was one more example, if you remember this one. So in this case, the you have removed this particular index, so the next available element is this. So this is the new value of s, right? So that's why you have to like have some kind of function here that will give you the next available element after a particular index, right? And this you can implement via a set or a linked list or anything of that sort. Basically, you just need what is the next available element after a particular index, let's say 1, right? Once you have get this particular s index, so in this case you will get like from this particular function you will get 4. Like let's say you are maintaining a linked list, so linked list would contain 1, 4 and 5. So after you have get this 4, you will actually have to figure out what is the value here because that would be the actual value of s, right? So it is very similar to you figure out that okay, I have to remove this particular index 3, but actual value of I here was actually 1, which is the value you get via segment tree. So that's what we are doing. We are just querying the segment tree for that particular index. Now after this entire loop ends, this answer variable would contain the required answer that we want, right? So hope this entire solution makes sense. If you have watched this till this point, I would strongly encourage you to pause the video and try to code this entire thing by yourself. If you don't know about segment tree, you can just copy paste the segment tree code from the description solution that I have pasted and code the rest of the solution by yourself. Notice that everything we have shown here except this next available, which you can implement via linked list or via a usual set and doing a lower bound or upper bound, right? So that is the only unknown, and I would strongly encourage you to code this entire thing by yourself. So next we'll be looking at the code. The code is exactly similar to what we have discussed. We have first figured out the array of indexes in which we will be removing the indexes. So we just push the value and the index and sorted it. And notice that we have to find out the next available index as well. So we are maintaining a set of available indexes. So whenever we remove a particular index, we'll remove that index from the set as well. So initially, set will contain 0, 1, 2, 3, 4, 5. When you remove the second index, you will remove that 2 from the set as well, right? Now, let's say you have to figure out the next index of 1. So you can just do a lower bound or upper bound of 2 and you will get the next available index of 1, right? So that's how we are like I'm finding out next available index, but you can do use linked list as well. Basically, you can simply maintain a double linked list and you can store what is the node address for each of these so that you can jump to this node directly in the linked list. Now, once you jump to this node, you can simply go forward and figure out what is the next element. And in the same way, you can remove a node as well from the linked list. So for this, we have this all indexes set. And after that, we are doing the exact same thing. We figured out the actual index, original index, which is like this array value 2031154. Now this actual index would be giving you this one, but you actually need this particular value here after you have done some subtraction or addition, right? So that's what we are doing. We are figuring out the index in the actual array. So sorted index is the name. This is actually the I that we are talking about in this particular pseudocode, right? After that, we just figured out what we need to add to our result. So this is like applying the algorithm I minus s plus 1 or I minus s. And then we update the segment tree starting at original index up to l minus 1. So basically index up to l minus 1. And then we figured out what is the next available index. So next available index, as we have said, we are using set. So we just do a lower bound of original index. And because original index is already removed, this lower bound will give you the next available index. And if it is giving us the end, we will just move to the first element of the set because that would be the next available index. And once we get out the value of the next available index, we actually need to figure out what actually exists at that index. So for that, we have queried the segment tree, right? And after this loop ends, the result will contain how many elements we have to skip. So basically, I'm not adding plus 1 here, right? So I've added plus 1 plus n at the end. Basically, one operation will be required to remove every element. So this result till now just contains what like how many operations or how many elements we have to skip, right? So next part is the segment tree, which is the standard segment tree of range update. Here we don't need two arrays. Basically, we don't need a lazy array for lazy propagation and a tree array because we actually don't need to query or we actually don't need to do a range query. Like the tree array is required only when you have to do some range query. Here we are doing point queries and hence we can just get away with single array. Either you can call it lazy or you can call it tree, right? So again, in the series, we haven't actually touched upon the range update part. So we can discuss that at sometime later, but this is the standard part where what we are doing at the time of initializing, we are building the tree, and building the tree is actually just initializing the tree with 0, 1, 2, 3, 4 minus, like this particular section. Like the first index is 0, 1, 2, 3, and so on. And after you have built the tree, the update part is exactly the standard one. We if the current range x to y doesn't lie in this particular node range L to R, we will continue. Otherwise, we will simply update the lazy and push it to the children's, right? And after that, we will, like, if both of the condition is not true, we will go in both left and right. So next part is the query part is exactly similar. Like here we have to do just point query. So the termination condition here would be L is equals to R, and we have to return lazy I at that particular case. And if that's not the case, we will figure out where exactly the given index lies, either in the left or in the right. If lies in the left, we will query the left half. Otherwise, we will query the right half, right? And this will finally give you the value at particular given index. And notice that we are, because we are pushing the lazies as well, so whatever lazy updates were remaining at the node in the path, those gets pushed as well to the uh, bottom of the tree as well, right? So this is like, I'm not explaining this in depth again, because this is standard stuff. If you have any particular doubts, you can ask them in the comment section below. I would have to answer. So that's pretty much it about the solution. If you have any doubts in the entire solution, I would encourage you to ask that in the comment section below. I can help answer that. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.